Let's start with an implementation of a tree in Python. We're going to start like fairly simple and build up on it as we go. So a tree, a recursive tree data structure, is going to have a root and a list of all the subtrees of that tree. Some things to note: if the root doesn't exist, then the subtrees must be empty. We must have a root if there are going to be subtrees there. And the subtrees may be empty even if the root does exist. This basically would mean you have a tree that has one node, and we'll use nodes here to represent sort of the elements of the tree. In the last one, in the last video, we had the little circles in the diagram to show all the spots on the tree, whether it was the root or parts of the subtree or the leaves. All of these are nodes, the same way we kind of think about them with a linked list. When we initialize a tree, usually we want to be given a root value. It can be none, though, in which case the tree is empty. Or if it is something, we're going to build a root and put it in there. If we want, we can also give it a list of subtrees. That could be empty. Definitely, if the root doesn't exist, it must be empty. However, if there is a root, we could have some other stuff that's there. Simple method: is this tree empty? Basically, is the root exist or not? Okay. Our initializer here always creates either an empty tree or a tree with a value and potential subtrees. It's possible for the root to exist and subtrees to be empty. This means you have a tree with just a root. That's it. As we'll soon see, the empty tree and single case values are generally the best cases when writing recursive code that operates on trees. Now, there's a reason we keep asking the same question: what's the relationship between a tree's something and the blank of its subtrees? I asked like 4 of those in the last video. Understanding the relationship between a tree and its subtrees, in other words, the recursive structure, helps us to make really simple, really elegant code for processing a tree, kind of like we did with the nested lists. So, first example. The size of a non-empty tree is the sum of the sizes of the subtrees plus 1 for the root. And the size of an empty tree is 0. Kind of makes sense? This observation immediately lets us write the following recursive function for computing the size of a tree, so length, which is the number of items contained in the tree. If it's empty, it's 0. You can see this as, kind of our base case. Otherwise, the size is going to be at least 1. We got the root there. And then for every subtree that we have, we add the size of that subtree. You can also use len of subtree here, because Python will allow you to use whatever method this is to substitute for the length function. And kind of like we did with our nested list before, this will help us compute the size of our recursive structure, in this case, our tree. So we can generalize this kind of nicely to a template for any recursive method on a tree. We have a function. If our tree is empty, we have some situation. Otherwise, set up some stuff. For each of our subtrees, call our function and do the same operation, and so on. Sometimes these ellipses here will refer to the root, sometimes they will not. Again, it kind of depends on what you're implementing. Now, often when dealing with trees, we like to think about the case where the tree has exactly a single item. So we can modify our length to handle this separately with an extra check. So in other words, the exact same thing here, but just for the case of making this maybe kind of easier to look at, we can have an extra if statement here that's if specifically our subtrees are empty, but the tree itself is not, the size is 1, because that means it's just the root. Now, sometimes you have to do this. It might be the case that you need to do something different for a tree that just has 1 item in it, or something different for when it's empty or when it has multiple things. Sometimes this is redundant. Maybe you don't actually care, and the recursive step might handle this for you. So, for instance, for length, figuring out the size, this is redundant. We don't actually need to have this code here. The single item case is already handled by the recursive step because we count the root in this line that I've highlighted. It will return 1 if there are no subtrees. When we do for subtree in the subtrees, well, there aren't any, so we just skip this whole block right here. However, the possibility of having a redundant case shouldn't discourage you from still considering to do this. Treat this as part of your editing process. It might be the case that this is extra code and you can get rid of it later, Or you might find at some point that this actually does provide you some value for some reason or another. Maybe you want to actually, output a text message that says the tree is empty. The tree is just a root. The tree is a root and has subtrees, the total size being X, whatever that is. So for reference, here is a 3-case recursive tree code template. If it's empty, do a thing. Otherwise, if it's just a single node, do a thing. Otherwise, do some stuff potentially. Because the elements of a list have a natural order, lists are kind of easy to traverse, right? You just have so you can have a string method that produces a string with all the elements. It's kind of easy. You just go through everything in order and you're done there. But how do we do it for trees? It's a little trickier, right? Going through a tree, you can't just follow a straight line. There's a bunch of paths you could take. So here's an idea. Start with the value of the root, then recursively add the string of each of the subtrees. It's not too hard to do. The base case is, the tree is empty. In this case, you don't return anything. So here is our implementation. If it's empty, you do nothing. Otherwise, our string is going to start out with the root, whatever that is. And then for each subtree, we're going to add on the string representation of that subtree. Now, consider what happens when we run this on the following tree structure. We have a tree that's 1, a tree that's 2, a tree that's 3. So these are all just individual nodes. And then we build a tree that's got a root of 4, and 1, 2, 3 are the children of that. Then we're going to build a new node, number 5. And then 6 is going to be a root node that connects this number 5 and then this tree we've built over here. And what happens when we print it? Well, we get 6, 4, 1, 2, 3, 5. Where do these numbers come from? Let's take a look. I'm going to grab this code and hope that it doesn't explode. Actually, let's start by grabbing the tree stuff itself. This is pretty important. I find that any tends to break stuff, so don't mind me just butchering some of the documentation here. It's all stuff you should have, but I just want it to work right now. Okay, and now let's go grab our string representation. I do hope this works. We're gonna find out. And sure, let's go run all of this. No idea what's going to happen. We're just going to find out. Take one of this, indentation. Yes, this should all be tabbed in. Still an indentation problem, probably because this should also be tabbed in. Okay, cool. 96, ooh, that's promising. Okay, I will skip a little bit through here. So we're going to build a bunch of nodes. Node. So we got one node here, that's 1, 2, 3. These are 3 nodes of our tree. Then we're going to have our 4th node. This is represented like really weirdly on here, but follow with me for a second. The root of this one tree is 4. It actually kind of has a little representation here of 1, 2, 3, where basically this root node that's the 4 has children 1, 2, 3. That's where all these arrows are. We probably could represent this with a little bit of a nicer diagram, but the key elements are there. We're going to have a 5. So here's our 5 down here. It doesn't have any children, neither do these. And then our 6th node is going to connect 4 and 5. Have we gone through there? Yeah, okay. So, and we actually can see what's going to happen with the print here. It's going to do 6, 4, 1, 2, 3, 5. It's actually kind of conveniently telling me already. since Python Tutor is handy about that. But anyway, 6, the root node of our tree that contains everything in some form or another, has 2 children. They are subtrees. The first one is our node number 4 that has the 1, 2, 3 connected to it. And the second one is the 5 that has nothing else. We try to print. This is where like it takes a lot of steps, it looks like. So first off, we start with the very beginning, which is the 6th node here. It is not empty, so we're going to need to do our recursive case here. Well, yeah, is empty. No, it's not. Okay, moving on. So our string is going to start out with the root, which is the 6. So you can see here we got the quotations and 6. For each subtree, the first subtree here is going to be our 4. So this arrow that I've highlighted in red here, pointing at the 4, this is where we're going to start out because that's the first subtree of our number 6. And we're going to try to figure out how to print that one. All right, here we go. So you can see from our global frame, which is like our main method, we're trying to print the whole tree. And to print the whole tree, we need to be able to print the 4. The 4 is non-empty, so this function is going to return false. 4, we start out with the number 4, and now for each of the subtrees of that, we need to do printing. The first subtree of our 4, as this red arrow shows us, is the 1 node that we made. Okay. Another string call. You can see we're kind of building up all the calls to making strings. Now this one should be a little bit easier. Is empty is once again false, because we got a node here. Okay, printing this out, we have a 1 to start. Now, the subtrees in this one don't exist. There aren't any. So we skip directly over this next call, and we are returning just the 1 that we have here. So now the call that we had before was s plus equals the string representation of our subtrees. So in other words, the 4 combined with this string representation. And we throw in some new lines here to make it a little easier to read. So we end up with 4, then 1. All right, we've printed the 4 and the 1. Now we need to add on, or not printed, but we've stored the 4 and the 1. Now we need to grab the 2. So the next subtree, you see this red arrow moves over to this spot. We're going to print the 2 out now, or we're going to get the 2's string representation. So, same steps we go through. It's not empty. We get the 2, and we return it. So now we have 4, 1, 2. So this red arrow next goes over to the 3. And you can kind of see the process here. We're going to get the 3. Since the 3 is not empty, we grab the 3. We return it. So now we got 4, 1, 2, 3. Okay, great. Now, this string computation that we've been doing was all originally called from our root of 4 of the subtree that we were working on, the 4 that's connected to 1, 2, and 3. But that wasn't where we started all this. We started all this off with the 6. So this 4, 1, 2, 3 gets brought back over to where our 6 started, and we combine it. Now we have 6, 4, 1, 2, 3. The 5's still hanging out, though. We need to go and visit that. So here, our subtree, which was the 4, is going to move. So the arrow now, that I've highlighted in red for a second here, goes down to the 5. That's this arrow. Printing that one's pretty straightforward. It's just going to be a 5. It's not empty. It's a 5. We throw that onto our 6, 4, 1, 2, 3, and we add the 5. There are no more subtrees, and so we are done. We return that, and hooray, we print out our 6, 4, 1, 2, 3, 5. Great. Now, it's all well and good that we know all the elements of the tree, but there's one thing we lost along the way, which was we don't actually know, just based on 6, 4, 1, 2, 3, 5, which are children's which are children of what? Is it the case that 6 has children 4, 1, 2, 3, 5? Is it the case that 6 has a child 4, which then has the children 1, 2, 3, 5? We're missing some stuff in here, right? The structure of the tree is kind of gone. So when you're using something like maybe PyCharm, which has a folder structure of files, indentation is one way you can differentiate different levels of the tree. So let's suppose we want our tree to actually do something like this. This kind of tells us, hey, 6 is the root, it's got children 4 and 5, and 4 has children 1, 2, 3. In other words, we want our string representation to return a string that has no indents before the root, 1 indent before the children, 2 indents before the children of those, and so on. Well, how do you do this? We need the recursive calls to act a little differently. They need to return strings with more indentation the deeper down we go. In other words, we want information about where a method is called to influence what happens inside, and that's the whole point of parameters. So we're going to pass in an extra parameter for the depth of the current tree, which is then used to add a corresponding number of indents before each value in the string that's returned. Now we can't change the way that the string method itself works, but we can use a helper method that has this extra parameter. So here's how we're going to do it. We're going to have a method called string indented. This is a helper method that will do the lion's share of the work that we're actually looking to get done. And it's going to take an extra parameter, which is the depth, returning an indented string representative of the tree where the indentation is specified by the depth. And so it looks pretty much the same as before, but here where we initialize the string based on the root, things look a little different. We're going to take a indentation, multiply it by how deep we are, and then add on the value of the root plus a new line character. When we make the call to to print out the subtrees, instead of printing out just the normal string representation, we'll use our helper and increment the depth as we go down. And now when we actually implement our string representation with the overloaded underscore underscore str underscore underscore, we're just going to directly call our helper. And so here's what will happen. Let's copy that in here. The indentation here is wrong. And our string method is simplified from this whole thing all the way down to just this. And, let's see what happens. That's what we're here for, right? 99 steps once again. So you can see probably that the steps that are taken are going to be kind of the same. We build our nodes. Here, I'm going to fast forward a little bit. Build our 1, 2, 3, 4, which is connected to 1, 2, 3, 5 connected to nothing, and 6, which is connected to that. And we can sort of, spoiler alert, skip our way to the end and see it's actually going to build exactly the string that we're looking for. And the way that it does that is, initially our depth is 0, so the first string that we're constructing is going to just be the same 6 that we were used to. Now when we do the subtree, we're going to look at the 4, non-empty, and the depth of the 4 is 1. So we want the 4 to be indented 1 level in. So before we just saw, quotation 4, new line character. This time, we're going to have quotation, indentation 4, and then the new line character. And when we look at 1, 2, and 3, we'll see, kind of unsurprisingly, when we try to print those out, because the depth is 2, we're going to have a double indentation. So quotation, 2 indentations, then the 1. And so, I encourage you, give this a shot so you can see the steps that are going through. Probably isn't sufficient just to look at the way that I'm showing it right now, because it's kind of, there are a lot of arrows here. I mean, just moving my mouse over and seeing how many are highlighted makes it kind of tricky to follow, but I do recommend you actually try running this yourself so you can kind of see where all these relationships are being drawn and how we construct these indentations. Definitely can't get it just from watching the video. Give it a shot on your own. Now, a quick technical note on optional parameters. One way to customize the behavior of a function is to make parameters optional by giving it a default value. This can be done for any function you want, recursive, non-recursive, inside a class, outside a class, and the syntax is really simple. We use it in the revised version of string indented to give a default value for depth. So the only thing that we've changed here is our depth is an integer that will be 0 if it's not defined. In this version of string indented, depth is an optional parameter that can be either included or not when the method is called. If you don't call it with a number, the depth won't be set to anything. If you call it with, the number 5, then depth will be 5. And when you call it without anything, the depth will be 0 because that's what we want it to be initially. Optional parameters are really powerful for Python. They help you write more flexible functions. They help you use methods in all kinds of situations, but there's two important things to keep in mind. First, optional parameters must appear at the end of your list of parameters. It's just a syntactical thing. And finally, you should not use mutable values like lists for optional parameters. If you do, the code will seem like it works and then suddenly doesn't. And if you're not sure why, you can either ask about this during office hours or, better yet, give it a shot yourself. Try it out and see why that might be the case. Instead of that, my recommendation is use optional parameters that have immutable values, either integers, strings, or none.